In this video, I'm going to go over the process of solving problems involving weak acids and weak bases. So remember when we talked about strong acids and strong bases, we learned that both of those are called strong acids and bases because they ionize completely, whereas weak acids and weak bases don't ionize completely. So as a quick review, if we had NH3 in solution, that's a weak base. If we let that come to equilibrium, at some point in time, we will have lost some NH3 and gained some of the products, NH4 plus and OH minus. Now the goal of this chapter will be to go through the process of calculating the concentrations of the products. Now we're most interested in either the concentration of OH minus or the concentration of H plus. Most notably the concentration of H plus, because in the end we will want to calculate the pH, and in order to do that we need the concentration of H plus. So if we have this chemical equation above, HNO2 plus H2O in equilibrium with H3O plus and NO2 minus, if we were to write the Kc expression, we would write the concentration of products divided by the concentration of the reactants. But in this case, since water is a pure liquid, that is not included in the equilibrium expression. So then what we would do, we would write Ka, and the A just means we're talking about acids. It's still an equilibrium constant. And we would not include the concentration of water in this equilibrium constant. So we just have the concentration of the products, which are H3O plus and NO2 minus, divided by the concentration of HNO2. So remember to calculate the pH of a strong acid. Since strong acids ionize completely, we can use the initial concentration of the strong acid to be the same as the concentration of H plus that will be produced. So we would just take the negative log of the concentration of the strong acid. If we want to calculate the pH of a weak acid, we have to calculate it by solving an equilibrium problem using an ice table as we did in the previous chapter. Now, to do this, we will have to be given an equilibrium constant, a Ka value, and sometimes that will be given to you in the form of a Ka, but other times you might be given a pKa. Now, pKa is similar to pH in that pH is the negative log of the concentration of H+, whereas pKa is the negative log of the Ka. And to calculate the Ka from that, we would just use this equation, Ka equals 10 to the power of minus pKa. So this table just shows some ionization constants of some weak acids, and the thing to notice is the Ka values for each of these acids. So notice they're not the same, which means that some of these weak acids have different strengths. And remember, the strength of an acid is dependent on how much it ionizes, the degree of ionization. So the same rules for equilibrium constant apply to this situation as it does for any other situation. An acid that ionizes the most will have a high Ka value or a high equilibrium constant, whereas an acid that doesn't ionize very much will have a low Ka value. So in this table here, hydrofluoric acid has the highest Ka value. So of these acids in this table, it's going to ionize the most, whereas phenol has the lowest Ka value and is going to ionize the least. So let's just do a quick example comparing the pH of strong acids and weak acids. So in this question, we're asked to compare a strong and a weak acid both at the same concentration. So for the strong acid, it's quite simple to determine the pH. Remember, the pH equals the negative log of the concentration of H plus, and the concentration of H plus for the strong acid is going to be the same as the concentration of the strong acid because that ionizes completely. So HClO4 will ionize completely and produce 0.1 molar H plus and 0.1 molar ClO4 minus. So we can just write the 0.1 molar directly in this equation. So negative log of 0.1 molar, and that's going to equal a pH of 1. Now, if we want to calculate the pH of the weak acid, we have to do something a little bit different. We have to solve an equilibrium problem. So the first step in any equilibrium problem is to write down the chemical equation. So we have HClO plus water in equilibrium with ClO minus and H3O plus. Now we set up the ice table. Okay, so initially we have 0.1 molar HClO, and since H2O is a liquid, we don't care about the concentration of that, so we're not going to put anything under the H2O column. ClO minus initially 0, H3O plus initially 0. We're going to lose some HClO, we're going to gain some ClO minus, and we're going to gain some H3O plus. So we're going to end up with the equilibrium conditions as follows, 0.1 minus X, and for the products, X for ClO minus and X for H3O plus. Next step, write the Ka expression. Ka equals the concentration of ClO minus times the concentration of H3O plus divided by the concentration of HClO. Ka is given in the question, 2.9 times 10 to the minus 8 equals x squared over 0.100 minus x. And we're going to assume that this x is negligible because we have a pretty low Ka value, pretty low equilibrium constant. So if we solve for x, the value that we get is 5.39 times 10 to the minus 5. And that's going to equal our concentration of H3O plus. Now to figure out the pH, we simply have to take the negative log of our concentration of H plus. So pH is going to equal the negative log of 5.39 times 10 to the minus 5. And that's going to equal 4.27. So just to recap, if we have a 0.1 molar solution of a strong acid, the pH is going to be 1. And if we have a 0.1 molar solution of HClO, the pH will be 4.27. Now, if we had a different weak acid, the pH would be a little bit different because it would have a different Ka value. But if we had another strong acid, such as HCl or HNO3, that pH would still be 1 because all of the strong acids ionize completely. So now let's quickly talk about percent ionization or degree of ionization. So this is just going to tell us how much a particular acid or base ionizes in solution. So the degree of ionization is the quantity of substance that is ionized. So in this case, that would be the amount of H+, for example, and that is divided by the concentration of the substance before it ionized. So in the previous example, if I just switch back to the previous slide, when we're looking at the weak acid, this would be the quantity of substance that is ionized. And in the question, this would be the quantity of the substance before ionization. So for degree of ionization, we would just take the concentration of H3O plus divided by the concentration of the HClO. If we wanted to determine a percent ionization, we would take that same fraction and simply multiply it by 100. Now, the percent ionization of a substance is not a constant number. It depends on the concentration of the substance that is in the solution. So if we have a high concentration of, for example, HNO2, the percent ionization is a lot less than if we have a low concentration of HNO2. So notice that this particular example, if we have a 0.1 molar solution of HNO2, we have approximately, we'll call it 8% ionization. Whereas if we have, say, 0.001 molar HNO2, then we have something like a 45% ionization. So this matters a bit when we're doing equilibrium calculations with weak acids and weak bases. Because remember in the last chapter when we were talking about when we can ignore that X in the equilibrium row of the ice table, we can usually ignore it when the equilibrium constant is pretty low, but it depends also on the concentration of the substance that we are talking about. So if the concentration is really low, even if we have an equilibrium constant of 1 times 10 to the minus 5, it still might ionize significantly, which might affect our final concentrations. So the answer to the question, when can I ignore the X, and again, I'm talking about this x down here, when can I ignore that x? The simple answer is if the percent ionization is less than 5%, then you can ignore it. So you can't just simply say if the equilibrium constant is less than 10 to the power of minus 5. That works most of the time, but not always. So if you really want to be sure that you can ignore x, what you can do is you can do this calculation like we did on this slide and ignore the x. And then when you solve for x, you can do the percent ionization calculation. And if that ends up being less than 5%, then you are safe to ignore x. If it ends up being more than 5%, then you have to solve the quadratic equation. So let's go through an example that shows the difference in the ionization between two different concentrations of the same weak acid. So calculate the percent ionization for 1.28 molar HNO2 and 0.0150 molar HNO2 solutions, and we're given a Ka of 4 times 10 to the minus 4. So again, this is a weak acid problem, and the first thing we should do is write down the chemical equation. So we have HNO2 plus water in equilibrium with NO2 minus plus H3O plus. And since we're trying to solve a weak acid problem, we'll set up an ice table, and we'll start with the 1.28 molar concentration. So 1.28 for our initial concentration of HNO2. H2O we don't care about because that's a pure liquid. And we can fill in the rest of the ice table as we always do. Now write out the equilibrium constant. So for both of these examples, we'll just ignore the x just to make the math a little bit more simple. So if we solve for x in this case, we're going to get 0.0226, and that's a concentration of our H3O plus, because x in the table equals the x that we just solved for. And now to determine the percent ionization, we're going to take x that we just solved for, divide it by the 1.28 molar initial concentration, multiply that by 100%, and then we're going to get 1.77%. So that's the percent ionization of the 1.28 molar solution. Okay, 1.77, and I'm just going to write that up here. So now let's do the same calculation, but instead of using 1.28 molar, we're going to use 0.150 molar. So I'm just going to replace the appropriate values in the ice table and in our equilibrium expression. And if we do this calculation, we end up with a different value, 0.00245 molar H3O plus. And to calculate the percent ionization of this one, we'll take the calculated x, 0.00245, and divide it by the concentration of HNO2, which in this case is 0.0150. Multiply that by 100%, and our percent ionization for this one ends up being 16.3%. So as you can see, we did the same calculation, just used a different amount of starting HNO2, and we got quite a different percent ionization. So in the first case with 1.2 molar HNO2, since the percent ionization is only 1.77%, we could ignore x. However, if we had 0.0150 molar HNO2, since we have such a high ionization of 16.3%, we would actually have to go through and solve a quadratic equation in order to get a more accurate answer for this particular concentration. So now let's talk about weak bases. The setup is pretty similar to that of a weak acid. The main difference is that instead of getting H plus in the chemical equation, we now have OH minus. So OH minus is going to be on our equilibrium expression, and instead of Ka, we have Kb. So Ka just means the equilibrium constant for an acid, whereas Kb means the equilibrium constant for a base. So to calculate the pH, the first thing that we're going to do is find the concentration of OH minus. So for weak acids, we found the concentration of H plus. Now we're going to find the concentration of OH minus. We're going to convert that to a concentration of H plus using the Kw relationship, which is on the next slide. And then from there, we have a concentration of H plus, so we can determine what the pH is. So as with acid problems, you may be given a pKb instead of a Kb. So the same equation as in the Kas. So the pKb equals the negative log of Kb, and Kb equals 10 to the power of minus pKb. Okay, so if you are given a pKb, you have to convert that pKb into a Kb in order to do the equilibrium problem. So if you remember back to chapter 14 when we talked about manipulating equilibrium constant expressions, that will help you understand this just a little bit more. So we know also from this chapter that water undergoes autoionization. So two waters produce an H3O plus and an OH minus. And we know that that relationship, we call that Kw, or the equilibrium constant for water. Okay, Kw equals 1 times 10 to the minus 14. Now, if we have a general weak acid chemical equation, we have HA plus water produces H3O plus and the conjugate base A minus. And from there, we can get a Ka. For a weak base, we have the weak base A minus reacting with water to produce OH minus and the conjugate acid. And from that, we can get the equilibrium constant for the base, or Kb. Now, if we add these two reactions together, notice what we get. The HA cancels out, the A minus cancels out, and we're left with two waters, one H3O plus, one OH minus, which is exactly what this equation is here. So if you remember from chapter 14, when we add two chemical equations together, we would multiply together the equilibrium constants in order to get the equilibrium constant of the overall reaction. Same thing here. Multiplying Ka times Kb is going to equal Kw. And that's a relationship that will become important if you are given, for example, Ka, and you need to calculate a Kb, or the other way around, given Kb and need to calculate Ka. So just like weak acids, weak bases also have different strengths, and it has to do again with how much it ionizes. So weak bases that ionize more will be stronger weak bases than those that ionize less. So in this example, we have ethylamine with a Kb of 5 times 10 to the minus 4 versus urea, which has a Kb of 1.5 times 10 to the minus 14. So in this case, the base strength is increasing from the bottom of that table to the top because the Kb values are increasing from the bottom of the table to the top of the table. So here are just a couple of equations that might come in handy when solving weak base problems. And in the next slide, I'm just going to go over an example. So let's do a similar example as we did when we were talking about a weak acid. So in this case, we're going to compare the pH of a weak base with a strong base, both at the same concentration. So we'll start off with lithium hydroxide, which is a strong base, and we know that's going to ionize completely to produce lithium plus OH minus. So if we start off with 0.2 molar lithium hydroxide, we're going to end up with 0.2 molar OH minus. So to calculate pH, the first thing we should do is to calculate pOH. So pOH equals negative log of the concentration of OH minus, which in this case is 0.2 molar. So if we calculate that, pOH ends up being 0.699. And then if we want to calculate pH, remember pKw equals pOH plus pH from the previous slide. pKw was 14. pH is what we're trying to solve for. So pH is going to equal 14 minus 0.699. And then our pH is going to equal 13.3. Okay, so that's the pH of 0.2 molar of a strong base. So now let's calculate the pH of a weak base at the same concentration. So we'll use NH3. So since it's a weak base, we have to first start by writing out the chemical equation. So here we have OH minus to calculate for. We don't have an H plus since it's a base. And let's do the ice table. So we start off with 0.2 molar. H2O doesn't matter because it's a pure liquid. Starting off with 0 of that, minus X plus X plus X, 0.200 minus x, x, and x. Okay, so in this case, we're given a pKb. So to do the equilibrium problem, we need a kb. So for pKb equals 4.76, to find the kb, we have to go 10 to the power of minus pKb. And again, the 10 in this equation is the inverse of your log function on your calculator. So kb equals 10 to the power of minus 4.76. kb equals 1.74 times 10 to the minus 5. So now that we have kb, we can solve the equilibrium expression. So kb for a weak base is going to equal, in this case, NH3 plus times OH minus over the concentration of NH3. kb is 1.74 times 10 to the minus 5. It's going to be x squared over 0.200 minus x. And again, we're going to ignore that x because we have a pretty low equilibrium constant. We can check it later if we want to see if it's 5% of the value, but it ends up working out. So now if we solve for x equals 0.00186. That's a concentration, again, because this x here is the same as this x here, which is a concentration at OH minus. Now what we can do is solve for POH. It's going to be equal to the negative log of the OH minus concentration. So our POH equals 2.73, and then pH is going to be the same as we just did previously, 14 minus 2.73, which equals 11.27. So again, with a strong base, we have a higher pH, right? We have more OH minus in solution, so a pH should be higher. In this case, it was 13.3. And for the same concentration of NH3, a weak base, we get a pH that is a little bit lower, of 11.27, right? It doesn't make as much OH minus, so it's not going to be as basic. It's not going to have as high of a pH as the strong base. Now again, if we had a different weak base, the pH would be a little bit different because our equilibrium constant, our Kb value, would be different. But if we had a different strong base, such as sodium hydroxide or potassium hydroxide, the same concentration would result in the same pH because they ionize completely. So that's all I have for this section. If you have any questions, please let me know.